Assalamualaikum and good morning. I hope all of you are doing well today. So we meet again this semester. I will cover part 2 simulation for chemical engineering. Right, so previously in part 1 you have used Super Pro software, right? But in part 2 we're going to use HYSYS software. So I hope all of you already familiar since you have used this previously in your second and third year of study, right? In material and energy balance and separation process course, right? Okay, in this course we are going to use HYSYS to solve some chemical reaction engineering related problems, and we are going to see the application of this software for process dynamics and control, and as well as plant design. So tools needed for this class, of course you need a laptop or PC, and then you need the software as well as the simulation module. So I have uploaded the module on the Google Classroom, so please download it there and follow the step given. Right. So what we are going to do in the first 2 weeks is we're going to solve a certain chemical reaction engineering problem using Aspen HYSYS. Alright, so this week 9, we're going to estimate the conversion in a continuous reactor reactor, and we're going to see the feasibility of CSTR if they are connected in series in order to achieve the desired conversion. And next week 10, we're going to estimate the reactor length required to reach the certain conversion, a desired conversion in plug flow reactor, and we are going to determine the heat in combustion reactor. So let's move to our first module, estimation of CSTR conversion. Okay, for example, you have this reaction. This is an isomerization reaction of cis 2 butene to form trans 2 butene. So given that this reaction follows first order reaction kinetics as shown here. Okay, given that the specific rate constant is equal to 0.23 per minute, or this is the value in per second. Now you need to determine the conversion achieved if we have two CSTR connected in series, given that each of the reactor has a residence time of 20 minutes. Assume that this process operates in steady state mode. Okay, using the analytical solution in reaction engineering, so you can calculate the conversion from the component balance in first and second reactor. Okay, the conversion here is 0.96, which is equal to 96%. If you have two CSTR connected in series. Now we're going to validate this value of conversion. Can we get the similar value if we use the software? So now let's open our Aspen HYSYS software and start by creating a component list of cis 2 butene and trans 2 butene. Okay, once we have added the component, now we can add our fluid package. Now we're going to use an RTL. Next, we're going to add the kinetic reaction. Double click reaction 1 and add the component which are cis butene and trans 2 butene. And then key in the stoichiometric coefficient. So negative value indicate the reactant, and the positive value indicate the product. And then the value of 1 is according to the reaction stoichiometry. And then given in the question that the value of K equal to 0.23, 1 equal to 0. If you substitute the value of E and B equal to 0 in this equation, you will simplify this equation and get K equal to A only, which is equal to 0.23. Then let's change this to pound mole per feet cube. Right. What else? Liquid phase reaction. Right. So we are ready to attach the reaction to our fluid package. Now we're going to enter the simulation environment and add the reactors lah. So you add 2 set of CSTR here. Now key in all the inlet and outlets. Right, next we add the reaction set. Next we add, we specify all the operating condition, temperature to be 25 degrees C, pressure to be 10 bar or 1000 kPa, and molar flow equal to 1 kgmol per hour. And don't forget to specify the composition as well. So feed consists of only 1 mole of cis-butane, and there is no trans-butane in our feed lah, because this is the product, right? Next we going to specify the volume. So we can add any volume here, because later we're going to create an adjust block and spreadsheet in order to find the required volume for the desired residence time of 20 minutes, right? Now we're going to add the spreadsheet first. Add the spreadsheet. And go to spreadsheet tab and enter this information. Now right click on the on cell B1 and add import variable. So we're going to add a CSTR1 tank volume. And then we're going to add the liquid volume flow to be, now right click and add import variable. So liquid 1 actual volume flow. So now we can calculate the residence time by dividing the reactor volume with liquid volume flow. So cell B1 divided by cell B2 multiply by 60 in order to convert hour to minutes. Right, next we're going to add the adjust block. So this is the adjust block because we want to adjust our CSTR volume in order to get the residence time of 20 minutes. So adjusted variable here is the CSTR tank volume. Click select. And then the target variable is the spreadsheet, or is the residence time, which is in the spreadsheet that we have keyed in earlier. And then the target value is 20. And you need to change the maximum iteration here to be like 1000. And then if you click start, the block should be solved, right? Okay, next. The first CSTR is now fully specified and has a residence time of 20 minutes. And okay, note that the vapor outlet stream has a flow rate of 0 because we only going to have the liquid product. Okay, now double click the second reactor and key in the inlet, which is liquid 1, and then this is vapor 2 and liquid 2, and then add the reaction set. Next, you need to specify the volume as well. Okay, now we are going to repeat the same procedure that we have done earlier by adding the spreadsheet and the adjusted block. You can just copy and paste to make it faster. But then you need to change this value. So add import variable. So you need to select CSTR1 tank volume, right? And then for liquid volume as well, add import variable and then liquid 1. Actual volume flow. And okay, the same equation applied. And then adjusted variable is CSTR, the second CSTR tank volume. And the targeted variable is the spreadsheet 2, residence time of reactor 2, right? has active and the process is converged. Okay, now check the result of stream liquid here. Wait, I think I have made a mistake here. This is liquid 1, this is liquid, this is liquid 2. So we need to change in the spreadsheet as well. So this is liquid 2, actual volume flow. This is already correct. And then at the adjusted block here, liquid targeted is okay, tank volume is okay. Okay, now process is already converged. Now we need to check the result of liquid 2 stream. Now go to the composition. Okay, alright, as you can see here, the mole fraction of trans 2-butene in the outlet stream is 0.96. Okay, right. If you check the reaction extent of each reaction, now check the reaction extent of each reaction, the total reaction conversion can be achieved. Now check the reaction extent. Okay, so the reaction extent of reactor 1 is 0.82, while the reaction extent of reactor 2 is 0.14. So adding these two values, you will get the value of your conversion, which is 0.968. So in this case, the total conversion, which is 0.968, is identical to the analytical solution that we have calculated earlier, meaning that we can use Aspen HYSYS software to solve the chemical reaction engineering problem. So that's all for today. We're going to continue with module 2 in a separated video, right? So thank you for your attention, and goodbye.